Hello, everyone. Today we are going to do chapter 3, which is over probability topics. So let's get started. So probability is something that you have been exposed to, whether you realize it or not. You probably even have an intuitive idea of how to do probability without really thinking about it. And so there are lots of different examples of probability, and we're going to deep dive into how to solve these mathematically. So 3.1 is just outlining the really important terminology. An experiment is a planned activity carried out under a controlled condition. So I like to use as an example of an experiment something like flipping a coin. Okay, so then an outcome is a particular result or experiment of an experiment. And so the outcomes of flipping a coin would be heads or tails, right? The event is a subset of the set of all outcomes of an experiment. The set of all outcomes of an experiment is called a sample space. So for example, our sample space, which is denoted by S, and when we list any kind of set or subset, we use curly braces to list it. So I'm going to use curly braces. Our sample space for flipping a coin is head or tails, right? Because those are the only two possibilities that you could get. They're the outcomes that are possible. Okay, so heads is an event and tails is an event. So a lot of times we use capital letters to signify events. So if I said H equals heads, this would be the event heads, and T equals tails. T would be the event of a tails occurring when you flip the coin. So the complement of the event, the complement of an event A consists of all outcomes that are not in A. So how we solve this mathematically is, what that means is A complement, when we're dealing with probability, would be 1 minus the probability of A. So for example, heads and tails are the only two possible outcomes for flipping a coin. So the complement of heads is tails in this case. And if you wanted to find probability mathematically, you could do that by doing 1 minus the probability of tails, and that will give you the probability of heads. So probability is a number between 0 and 1 inclusive that gives the likelihood that a specific event will occur. The foundations of statistics is given by the following 3 axioms. Let S denote the sample space, and A and B are 2 events in S. Then 0 is less than or equal to the probability of A, which is less than or equal to 1. So this is really important. What this means is that you can't have a negative probability. And you can't have a probability greater than 1. If A and B are any 2 mutually exclusive events, then the probability of A union, this is called a union. We're going to talk about this more in depthly in a minute. A union B equals the probability of A plus the probability of B. And we're also going to talk about what mutually exclusive means in a minute as well. This is the symbol for a union. Okay, and the probability of the sample space equals 1. So the probability of all the outcomes occurring is always 1. Okay. equally likely. Each outcome of an experiment has the same probability. So the probability of flipping a heads is the same as the probability of flipping a tail. So the probability of flipping a coin is equally likely. When you flip a coin, you will have, it's equally likely that you'll flip a heads or a tails. Conditional probability, the likelihood that an event will occur given that another event has already occurred. So for conditional probability, you'll see that I have two definitions here. This one, the first definition is explaining what conditional probability is. The second one is showing the mathematical notation for it. So the probability of, so this is read as the probability of A, and then this symbol right here means the word given, B. And all this means is that we want to know, if we already know B occurred, then what's the probability of getting A? Okay. All right, so the intersection A intersect B is an outcome in an event A intersect B is the outcome in both A intersect B are the same, okay? So what that means simply is that this intersection here, this is an intersection symbol. And the intersection symbol means the word and. Okay. Okay. So what that means is that for something to be in the intersection, it has to both be an A and B, because again, that means the word and. Okay. The union A union B is an outcome, is the event A union B is the outcome if A or is in B or is in both A and B. Okay, so what this one means a little more clearly is this symbol here is a union. And the union means that for an event to be in A union B, it has to be in A or B, because the union means the word or. So odds are not the same as probability. Odds is what we use to determine chance. And chance and probability often get confused, but they're very different. So the chance of something happening is a percent, okay? The probability of something happening is either a fraction or a decimal. So you have to realize that probability is represented by a fraction or a decimal, which makes sense, right? Because it falls between 0 and 1. And so that makes sense as an answer, right? And then the chance of something happening is a percent. Okay. Odds are often shown in ratio form. It's a ratio. Okay. So it looks like a fraction, but it's important to realize that it is a ratio. Okay. And so another way that you could write this to show that it's a ratio is the probability of A ratio 1 minus the probability of A. Okay. The odds in an event presents the probability as a ratio of success to failure. This is common in various gambling formats. Mathematically, the odds of an event can be defined as the probability of A over 1 minus the probability of A. Well, we talked about in this previous slide that 1 minus the probability of A is just A complement. So that's all you're finding when you're doing the ratio. You're simply doing the probability of A over the probability of A complement. Or again, you could write it as the probability of A with the ratio of probability of A complement. Okay. So the sample space S is the whole number starting at 1 and less than 20. Okay, so this is an example. We're going to answer these questions as we go. So the sample space S is the whole number starting at 1 and less than 20. So we need curly braces to denote a sample, and we want to start at 1, and we're counting. Whole number means that it's a counting number, so we're counting until 1 less than, until we get right up to 20, and 20 is not included because it says less than 20. So we have 1, 2, 3, 4, 5, 6, all the way to 17, 18, 19, right? And so this ellipse, I think it's called an ellipses. Yeah, this ellipses means that it's going to continue in the same pattern, and then it will eventually end. Okay, let A equal the even numbers and event B equal the numbers greater than 13. So if A are the even numbers, then we're talking about 2, 4, 6, 8, 10, 12, 14, 16, and 18, because we're only going up to 19. And B is the number greater than 13. So that would be 14, 15, 16, 17, 18, and 19. If we want the probability of A, so when we're talking about the probability, it's simply the probability of an event is the number of ways A can occur over the total number of outcomes. Okay, so if we want the probability of A here, we can see how many values are in A. Okay, so we see we have 1, 2, 3, 4, 5, 6, 7, 8, 9 values in A over the total number of outcomes. Well, the total number of outcomes is all the possible numbers between 1 and 19. And so that would be 19, right? 19 values. So the probability of B, again, it's the total number of B outcomes. So 1, 2, 3, 4, 5, 6 over the total number of possible outcomes. So the total number that's in the sample size, which is 19. Okay. A intersect B. So A intersect B, remember that the intersect means the word and. So it has to be in A and B. So let's look here and do some, I'm going to highlight so we can see. If we're looking at A and B, they share the numbers 14, 16, and 18. Those are the numbers that they share. And so the word and means that it's in both of them. So they share those. So that's going to be our set. So A intersect B is a set that contains 14, 16, and 18. So A or B, A or B. And so the word or, remember that the word or is a union. Okay, that's a union. Okay, so A or B means a union. So that's the probability. A, write that again. So that's A or B. Okay, is one way it could be represented. So A or B is going to be any number that's in each of these, but you don't have to list any numbers twice. So that would be 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18, 19. And so again, all we did there is we're looking at anything that's in either one of these. So all of these numbers are in here. So I listed all of them. And then I didn't have to list numbers twice. So I already listed 14, 16, and 18. So I also listed 15, 17, and 19. Okay. So if we want the probability that A intersects B, A intersects B has 3 values in it. So 1, 2, 3. We see here 1, 2, 3. And again, the total number of possibilities is 19. So the probability is 3 over 19. A union B, same thing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 possible values. And there are 19 values in the total sample space. A complement. So A complement is going to be everything that's not in A. So we see that A is the even numbers. So A complement is going to be the odd numbers, right? So 1, 3, 5, 7, 9, 11, 13, 15, 17. I'm going to continue. Oh, I can fit that last one. 19. There we go. So the probability of A complement, remember, is 1 minus the probability of A. And we've already found the probability of A. So 1 minus 9 over 19. Remember from your fraction rules that 1 can be represented as a fraction as whatever our number is of our totals over itself. So minus 9. So we get 10 over 19. And we could make sure that was true by counting these and making sure that we have 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we do. So our probability is 10 over 19. So what's the probability of A plus the probability of A complement? So the probability of A we found was 9 over 19 plus the probability of A complement is 10 over 19, which equals 19 over 19, which equals 1. And that makes perfect sense, right? Because all we did here was we know from our complement rule that these should be the same, right? If we have 1 minus P of A, that's going to lead to P of A plus P of A minus 1, right? All we did was solve this, okay? So you see how these are giving you the same thing, okay? It's just one's being solved for 1. All right, so let's look at conditional probability. So if we want A conditioned on B, now remember conditional probability means what's the probability of A occurring knowing that B already occurred, okay? So here, A represents the odd number. So what's the probability of getting an odd number knowing that you're only talking about numbers greater than 13? So you're looking only at B. So that's going to be your bottom number now, is whatever is in the total amount of B. So 1, 2, 3, 4, 5, 6 in B. So that's going to be our bottom number. And then A is how many odd numbers are in B. So we have an odd numbers? No, even numbers. A is even numbers. Even. So the even numbers are 14, 16, and 18. So we have 3 over 6. okay, which we can reduce, right, to 1/2. So then the probability of B given A is the probability of getting a number greater than 13 when we know we already got an even number. So we're doing the same kind of thing. We're just looking at A as our bottom. So the total number for A is 9. And we want to see how many numbers greater than 13 we have. And we have 3 numbers greater than 13. So that's 3/9, which we can reduce to 1/3. And we see here that these probabilities are not equal. So it's important to know that the probability of A minus or given B is not always equal to the probability of B given A. Okay, so I would write this somewhere in my notes to make sure that I don't, a lot of students want to make those two things equal because they look similar, but they're not the same thing. Okay, so let's look at 3.2 example. A fair 6-sided die is rolled. Describe the sample space S and identify each of the following events with a subset of S and compute its probability. An outcome is the number of dots that shows up. Okay. So event T, the outcome is 2. Okay, so let's think about our sample space, just so we have that. Our sample space when we roll a fair die, 6-sided die, is 1, 2, 3, 4, 5, 6. Okay, so if I want to list what T is, how you get T, the outcome is 2. So the only possibility is 2. Okay, so if we want the probability of T, then there's only one number in T, and there are 6 numbers in S. So our probability is 1/6. So event A, the outcome is an even number. So on a 6-sided die, we have 2, 4, and 6. So the probability of A is the total number that we have. Is the total number that we have in A, which is 3, over the total number of possibilities, which is 6. So if we reduce, that's 1/2. Event B is the outcome is less than 4. Okay, so B equals outcome is less than 4. So we have 1, 2, and 3 in our B. So the probability of B is 3 because we have 3 possibilities in B over 6 because there are 6 possibilities in our sample space. So again, we reduce and we get 1/2. So we want the complement of A. So the complement of A complement equals, while I'm thinking about this, A complement can be denoted several different ways. So let's go back up here where we talk about the complement of A. It could be denoted as A complement. It could be denoted as A complement this way, or it could be A complement as a tick mark. Okay, so those are how you usually see A complement. I prefer the A to the C to represent A complement, but you could see it any of these 3 ways in the future. Okay, so now back to this A complement. So we want everything that's in the sample space that's not in A. So that would be all the odd numbers, 1, 3, and 5. Okay, so the probability of A complement is again 3/6. And we could have found that so many ways. We could have done 1 minus the probability of A. We could have looked at the fact that A complement has 3 values and the sample space has 6 values. Or we can double check and add these 2 together to make sure they equal 1, and they do. Okay, if we want A complement B, So the way A complement B can occur is if we're looking at B, we only want things that are also in A. So that would be 2. 2 is in A and B. So that would be 2. And this is where the probability, you have to pay close attention. Remember, the bottom number, the total for the bottom number becomes whatever this value is. So B has 3. And then we only have one value that is in A. So B complement A, or B given A. So now we're looking at A and we only want what it shares with B, which is 2. Right, this should be the probability of A given B is 1/3. And here the probability of B given A is we have 1 value over 3 values here. Now, in this case, these two do equal, but that is not always true. And we will talk about in a minute when they are equal and when they aren't equal. Okay. So A intersect B. So A intersect B is whatever A and B share. Well, we already circled that when we did the conditional probabilities. They share 2. But the probability of A intersect B is different from this probability of 1/3 because we are now looking at A intersect B. What they share is 1 over the total possibilities in the sample, which is 6. So A union B. So we want to put everything that's in either one of them. So we have 1 in B, we have 2 in both of them. We have 3 in B, we have 4 in A, and we have 6 in B. I'm sorry, 6 in A. And so the probability of A union B equals, we have 1, 2, 3, 4, 5. Total outcomes for A union B, and then we have 6 total outcomes in our sample size. So it's 5, 6. If we want to find A union B complement, well, we can think about it this way. We can find B complement. So we know B complement is 4, 5, 6. So if we want A union B complement, then we're looking at what overlaps between A and B complement. And so that is, it occurs in either one of them, 2, 4, 5, and 6. And so the probability of A union B complement equals 4/6, which can be written as 2/3. Event N equals the outcome is a prime number. So if you don't remember from algebra, a prime number is a number that only has factors of 1 in itself. Okay, so from 1 to 6, our prime numbers are 2, 3, and 5. And so the probability of getting a prime number when you roll a die is 3/6, or 1/2. Event I is the outcome is 7. So in this case, I equals 7. And the probability of getting a 7, well, we know there's not a 7 on a number die. So this is impossible. So it's going to be 0. So we should really write this as an empty set because there is no value on a number die that is 7. Okay. All right, so 3.2 is talking about independent and mutually exclusive events. So let's talk about the difference between dependent events and independent events. Dependent events, if two events are not independent, then we say they are dependent. So let's see what does it take to be independent? Independent events. The occurrence of one event has no effect on the probability of the outcome of another event. Event A and B are independent of one following if one of the following is true. So the probability of A conditioned with B equals the probability of A. The probability of B conditioned with A equals the probability of B. Or the probability of A intersect B equals the probability of A times the probability of B. And so you have to show one of these three things if you are claiming independence of two variables. So an example of some independent things, if we roll, every time we roll a die, or every time we flip a coin, no matter what you get the first time you roll a die, it won't affect what you get the second time you roll a die. The same thing with flipping a coin. Whenever you flip a coin, whether you got heads or tails the first time will not dictate whether you get heads or tails the second time, right? But dependent events is when they're not independent. So a lot of times we're talking about replacement and not replacement when we're talking about dependent versus independent. So for example, if I drew a card from a 52 deck of cards and didn't put it back and then drew another card, then those events would be dependent because the probability of drawing the second card is affected by what I drew the first time around. Okay. And so mutually exclusive events means that the events don't have anything in common. So that means that when you say and, there's nothing and, right? So it can't happen. For example, if I roll a die, rolling an even and an odd when rolling a die one time is impossible. Okay, a number cannot be even and odd, right? It can only be even or odd. So with that being the case, it would be a mutually exclusive event. So that's an example of a mutually exclusive event. And so when we have events that are mutually exclusive, we can show this just like we could show independency with one of these three. We can show that events are mutually exclusive when we find the probability that A intersect B equals 0. So sampling with replacement versus sampling without replacement. If each member of a population is replaced after it is picked, then the member has the possibility of being chosen more than once. So that's sampling with replacement. A lot of times we talk about if we're sampling, like when you're pulling marbles out of a bag or something, if you put the marble back in the bag, then you're using replacement. If you're sampling without replacement, then you're keeping whatever you pulled out. So when sampling is done without replacement, each member of the population may be chosen only once. Okay. So I've noticed over the last several years of teaching that not all students know what's in a standard deck of cards. And in probability, we use that as an example a lot because it's just an easy way to come up with examples. There's so many different probability examples you could come up with from a standard deck of cards. You know, there's whole games like poker that are based off of probability when it comes to cards. So I just like to put this slide on here so that you are aware of what the lingo is when we're talking about cards. So there are 52 cards in a deck. There are 4 suits, and so these represent the 4 suits. They are clubs, heart, spades, and diamonds. And then we have 13 cards per suit. So there are 13 cards in each one of the suits. Okay. And so those are ace, and then 2 through 10, and then jack, king, and queen. And Jack, Queen, and King are called face cards. Okay. So your face cards are here. All right. And then a lot of times we talk about red cards versus black cards, right? And so there are 26 red cards and 26 black cards because the deck is evenly split between red and black. All right, awesome. So let's take a look at this example here, 3.8. Roll one fair six-sided die. The sample space is 1, 2, 3, 4, 5, 6. Let event A equal a face is odd. So then A is 1, 3, and 5. Let event B equal a face is even. Then B is 2, 4, and 6. Find the complement of A. So if we want the complement of A complement equals 2, 4, and 6, right? It's anything that's in the sample space that's not an A, which we see here equals B. Okay. Let event C equal odd faces larger than 2. So then C is 3 and 5. Let event D equal all even faces smaller than 5. Then D is 2 and 4. Are C and D mutually exclusive? So remember, mutually exclusive means they do not share anything. So if we're looking at C and we're looking at D, they don't have any numbers in value that are valued the same. So yes, these are mutually exclusive. And so if we were trying to say why it was mutually exclusive mathematically, we would go back to our rule. Mutually exclusive means that the intersection equals 0 because what they share, they don't have anything in common. So the probability of C intersect D equals 0. And so if I ask why or why not, that's what I'm asking for, the justification, the mathematical justification. Okay. Let event E equal all faces less than 5. Are C and E mutually exclusive? So now we're comparing C and E. So we're looking at E and we're looking at C, and we see that they do have something in common, right? C and E have 3 in common. Okay, so the answer is no, they're not mutually exclusive. And that's because the probability of C intersect D is not equal to 0. All right. So 3.4 talks about two main ideas. The first one is probability trees. So we often use probability trees to help us find sample spaces when it's a little difficult to visualize what the sample space might be. So here's an example. And this is if we flipped a coin 3 times. Okay, so if we flipped a coin 3 times, we could get heads or tails the first time. And then the second time, regardless if we got heads or tails the first time, we could get heads or tails. And then the third time, regardless if we got heads or tails on the first 2, we would get heads or tails. So then this tree, these are the branches. This branch gives you the outcome HHH. Okay. This branch gives you the outcome HHT, and so on and so forth. And so you can see here when we flip a coin, our sample space for flipping a coin is heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. And so our sample space has 8 possible values, right? 8 possible values. All right. So the second idea in 3.4 that is important is contingency tables. And contingency tables is the method of displaying a frequency distribution as a table with rows and columns to show how two variables may be dependent upon each other or contingent upon each other. And so you'll see here what happens is if we have dogs and cats and we're comparing male dogs and male cats and female dogs and female cats. So here you can see that these two different things, whether they're male or female, is independent, right? Independent of each other. Whether they're a dog or cat is independent of each other, right? But a male dog is not independent of each other. Those could be dependent. Oh, I've got my got my words backwards. Okay. I was thinking about mutually exclusive, right? So you can't overlap here. So these are mutually exclusive. And this cannot overlap as far as animals. So it is mutually exclusive. Okay. But whether they're independent or dependent, if the dog is a male dog, then it's not going to overlap with a male cat. But if we're just talking about dogs, a dog can be male or female, and so that could be dependent. So let's take a look at an example here, and this will kind of clear up how that looks. Okay, so calculate the following probabilities using the table. So we want to find the probability that the driver is a cell phone user. So if we're looking at cell phone users, we're going to look at the total number of cell phone users, which is 305, over the total number possible, which is 755. And when we're doing probabilities, you either need to give a decimal answer or a fraction answer. And if you give a fraction answer, a lot of times we ask for the most simplified answer. Okay, and so if I simplify this, this will be 61 over 151. Find the probability that the driver had no violations in the last year. So no violations total is 685 over the total is 755. So again, we can reduce to get 137 over 151. Find the probability that the driver had no violations in the last year and was a cell phone user. So this time, let me change colors so we can see a little better. So we want and, so where they overlap. So the driver had no violations and was a cell phone user. So that's right here, 280. 280. Over, again, the total is 755. We can reduce, which is 56 over 151. Find the probability the driver is a cell phone user or the driver had no violations in the last year. So if we think about this, this one's a little tricky. So let's think about this. So if they're a cell phone user, then we're looking here at this total. And if they're a driver who had no violations in the last year, then we're looking here at this total. But we see that we overlap at 280. Okay, so we don't want to include the 280 there more than once, right? So if we wanted to know what this value is, we could write it as cell phone users is 305 over 755 plus No speeding would be 685 over 755 minus, we take away where they overlap so that that's not counted twice. So 280 over 755. And so we get 710 over 755, which equals 142 over 151. Okay. So find P, the driver is a cell phone user, given the driver had a violation in the last year. So remember that when we're looking here, we're now changing what our total is supposed to be, right? So if we're looking here and it says the driver is a cell phone user, given the driver had a violation in the last year. So we already know that they had a violation. So we're only looking here. We're only looking here in green, okay? Which means that when we're looking at our probability, the cell phone user is, oh, we're only looking at green. The cell phone user is 25 out of 70 now, because we already knew that the violation happened, that they did have a violation. So that's 25 over 70. So 25 over 70 reduced is 5 over 14. And then we want to find the probability that the driver had no violation last year and the driver was not, given that the driver was not a cell phone user. So this time, let me erase because my graph is getting kind of messy. So this time what we're looking at is we know that the driver was not a cell phone user, And so the driver had no violations last year. So no violations last year. And we knew that they were not a cell phone user. So we get 405 over 450, which is 9/10. Okay. All right. So let's continue on. So a lot of times when we're using sets, which is what we use in probability, there's a whole section of mathematics called set theory, and we use that for probabilities. And so when we have set theory, we often use Venn diagrams to represent that pictorially. And so that gives us a kind of idea of what's going on here. So let's just talk about these different spaces and what's being represented, right? So if I wanted A intersect B, I'm looking where my two circles overlap. And so my A intersect B would be the set that contains 6. If I want just my set A, then I'm looking at everything that's in the circle of A. So that's 1, 2, 3, 4, 5, and 6. If I want my set B, it's everything that's in the circle of B. So that's 6, 7, 8, 9. Okay. If I want A complement, then that's everything that's not in A but is everywhere else. So that's all of this. So A complement would be 7, 8, 9, 10, 11, 12. Okay. B complement. Okay. Let me do some erasing so we can see clearly. B complement is everything that's not in B, but is in the rest of the space. So that would be 1, 2, 3, 4, 5, 10, 11, 12. Okay. A union B. is anything that falls in A and B. So we're looking at this entire thing here. We only have to list it once. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right. So this leads us to talk about the two basic rules of probability. The first one is the general rule of addition. And so that is what we've been calling union. Okay. We use addition when we're talking about the word or. So the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. And that's because of this Venn diagram right here. We know that or is the entire thing here. But if we didn't draw the picture and we were just looking at the numbers and we said, okay, A, the probability of A plus the probability of B, we then do A intersect B twice. It gets written over twice. So for example, if I did this in color, for those who are more visual seers, if I said, okay, just A and then plus B, we see that the intersection gets counted twice because it's green. It's not blue or yellow, it's green. So it was colored in twice. So we don't want to count that twice when we talk about the probability, so we have to subtract it away. Okay. So you want to make sure that this is in your notes. This is extremely important. You're going to use it over and over again. Now, this is where mutually exclusive comes in, right? If these were mutually exclusive events, then what would happen is in our picture, in our Venn diagram, if these were mutually exclusive, A and B wouldn't share anything. So they wouldn't intersect. So in that case, what happens is this value here just becomes 0. And so when you're dealing with mutually exclusive events, you just have to worry about P, the probability of A plus the probability of B. And this is only when it's mutually exclusive. The rest of the time, you have to make sure you take away that. So it's safest to just use this formula in general, because if they are mutually exclusive, you can just put in a 0 right here. There's nothing that they share. And so when we put in a 0, it doesn't affect our math, right? When we're doing adding and subtracting. Okay, great. So the next really important rule for probability is the multiplication rule. And so this is the rule for when we're talking about the word and, or when we're talking about unions. Remember, so the probability that A, or intersections, I'm sorry, A intersect B. Okay, A intersect B. So if they're independent, then the probability of A, you're just going to do the probability of A times the probability of B. If they're dependent, then you have to do the probability of A times the probability of B given A. And that's because the probability of B is affected by the probability of A, okay, already occurring. All right. And so these are our two multiplication rules here. And you can see here that from your multiplication rule, you could find your conditional rule, okay? So conditional probability this rule right here for dependent events will give you this here, okay? So if you just look at solving this, if we want the probability, if I solve this here for the probability that B given A, then I would have to divide both sides. Let me move this out of the way. I would have to divide both sides by the probability of A. And here it would cancel and you would get the probability of A intersect B over the probability of A. And so you see here, that's what's occurring. Pictorially, we are representing the probability of a conditional probability when we take away this intersection out of what is in B. Okay. So now we're just going to do several examples. So you'll see we have several examples. We're going to work through them for the rest of this video. So you can follow along with the examples if you would like. I encourage you to, so that you're well prepared for your homework. You could, if you need more examples, you can also go to your book, and there are more examples in your book. I just chose a few examples out of your book. I did not do all of the examples from your book. So if you went back and did your reading, you would see there are many more examples you can work on to test yourself and see that you're grasping the concepts. Okay, so let's jump in and do these examples. So we want to flip two fair coins, find the probability of the events. So I'm going to go ahead and draw a tree diagram so that I can know exactly what my sample space is here. So if I flip the first coin, I could get tails or I could get heads. If I flip the second coin, regardless of what I got for the first coin, I could get tails or I could get heads. So my sample space for this problem is tails, 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 heads, heads, tails, and heads, heads. I made my screen jump. So heads, tails, or heads, heads. Okay, so that's my sample space. So for A, it says, let F be the event of getting at most one tail. Okay, so let's just list what's in F then. So it's easy to find the probability, right? So what is in F? So at most one tail, which means it has 0 tails or 1 tails. So we have, you can get that by tails, heads, heads, tails, or heads, heads, right? So if we want to find the probability of F, we see that there are 3 possible outcomes that we could get over the total number of outcomes in our sample space, which is 4. So we get 3/4. So B says, let G the event of getting 2 faces that are the same. So there's 2 ways to get 2 faces that are the same, right? You could get tails, tails, or you could get heads, heads. Okay. So for B, the probability of G equals, there's 2 possibilities for our outcome of our event, and there are 4 possibilities in our sample space. So when we reduce, we get 1/2. C, let H the event of getting a head on the first flip, followed by a head or tail on the second flip. Okay, so for H, we're looking at, we know we got from the first one, flipped, followed by, okay, hold on, the event of getting a head on the first. So that's head. So we're looking here, right? Head first, and then you could get a tail or you could get a heads and heads. Okay. So the probability of C, the probability of H is there are 2 outcomes out of 4 possibilities. So again, 1/2. So D, are F and G mutually exclusive? Are F and G mutually exclusive? So remember, if they're mutually exclusive, their sets will not overlap. So let's look at F and G. F and G is right here, and they do overlap. They have HH, right? So the answer is no. And if I asked you why, you could say they share HH, or remember that the mathematical way of representing this is the probability of F and G intersect does not equal 0. So it is not mutually exclusive. Okay. Let J be the event of getting all tails. So J equals tails, tails, right? You get all tails, it's tails, tails. Are J and H mutually exclusive? So H is heads, tails, and heads, heads. And the answer there is yes, right? Because they do not have anything in common. And so mathematically, we would say the probability of J intersect H is 0. They don't have anything in common. Oh, that's E, not C. All right, let's look at the next example. So the next example we're going to do is 3.9. In a bag, there are 6 red marbles and 4 green marbles. The red marbles are marked with the numbers 1, 2, 3, 4, 5, and 6. The green marbles are marked with the numbers 1, 2, 3, and 4. A red marble is denoted by R, a green marble is denoted by G, and O, it represents an odd numbered marble, okay? The sample space, S equals R1, R2, R3, R4, R5, R6, so all of the marbles, right? S has 10 outcomes. What is the probability of getting a green marble that is odd, that has an odd number on it? A green marble that has an odd number on it. So this probability, green and odd, or green intersect odd, is we're looking at green marbles only, and they have odd numbers on them. So we have 2 out of 10, which reduces to 1/5. Okay. Let event C, taking an English class, C equals taking an English class. Let event D equal taking a speech class. Suppose the probability of C equals 0.75 and the probability of D equals 0.3. The probability of C intersect, or C given D, is 0.75, and the probability of C intersect D is 0.225. Are C and D independent? Okay, are C and D independent? So let's go look at what it says for independency. Let's just back up and take a look at independency. What are the 3 things we can check for things being independent? So if they are independent, these are the 3 things we can check. The probability of A given B equals the probability of A. The probability of B given A equals the probability of B. The probability of A intersect B equals the probability of A times the probability of B. So let's go look down here and see again how that question was worded. So are C and D independent? So we have the probability of C given D, okay, equals 0.75, and the probability of C equals 0.75. So yes, because it falls under the conditional probability rule. So A is yes, And we represent that mathematically by saying because the probability of C given D equals the probability of C. Okay. Are C and D mutually exclusive? So remember, for mutually exclusive, that means they cannot share anything, which means the intersection has to be 0. We would then be able to say clearly, because this is our intersection, that the answer is no, because the probability of C intersect D does not equal 0. Okay. What is the probability of D given C? So the probability of D given C. If you go back and look at your rules for conditional probability, the conditional probability rule is the probability of C intersect D over the probability of C. So the probability of C intersect D is 0.225. And the probability of C is 0.75. So 0.225 divided by 0.75 is 0.3. Okay. So let's look at 315. Okay. Carlos plays college soccer. He makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in a row in the next game. A equals the event Carlos is successful on his first attempt, so the probability of A is 0.65. And B is the event Carlos is successful on his second attempt, so B equals 0.6. The probability of B equals 0.65. Carlos tends to shoot in streaks. Carlos tends to shoot in streaks. The probability that he makes the second goal, given that he made the first goal, is 0.90. So what is the probability that he makes both goals is the first question. Probability that he makes both goals. So if he makes both goals, then mathematically we represent that as the probability that A intersect B, right? Because to make both, he would have to and. He made the first one and the second one, right? To make both. So remember that you can find the intersection by the probability of B given A times the probability of A, right? And we have the probability of B given A, and we have the probability of A. So the probability of B given A is 0.9, and the probability of A is 0.65. And so when we multiply, we get 0.585. Part B, what is the probability that Carlos makes either the first goal or the second goal? So again, this is the word or here. And so that would be A union B. Okay. And so remember, A union B is the probability of A plus the probability of B minus the probability of the intersection, A intersect B. So the probability of A is 0.65. The probability of B is 0.65. And the probability of A intersect B we just found was 0.585. And so the probability of A union B is 0.715. So C, are A and B independent? Are A and B independent? Okay. And we can say no, A and B are not independent, right? Because B intersect A, because A intersect B does not equal 0. Does not equal 0. Okay. So then D says, are A and B mutually exclusive? Oh, wait, I gave the wrong justification. This is the justification for mutually exclusive, right? So the answer is no, they're not mutually exclusive because A intersect B does not equal 0. or does not equal 0. And then the justification for independence. Let's go back and look at our independent rules, just because that's the one that's kind of tricky. It trips people up. So let's go back and look at it. So for it to be independent, A intersect B equals probability of A. Probability of B conditioned on A equals the probability of B. Probability of A intersect B equals the probability of A times the probability of B. So let's check that last one, right? We have A and B. We know what they are. So let's check it. So over here, I'm going to check independence. So for it to be independent, the probability of A intersect B has to equal the probability of A times the probability of B. Okay. Well, we know the probability of A intersect B is 0.585, okay, because we found it in A. So let's look at what A times B is. So the probability of A times the probability of B is 0.65 times 0.65, okay? So if we did 0.65 times 0.65, I didn't pre-do that. Let me check it real quick. So 0.65 times 0.65 equals 0.4225, okay? And 0.4225 does not equal 0.5855, okay? So the answer is no, because the probability of A intersect B does not equal the probability of A times the probability of B. So let's look at this example here. A community swim team has 150 members. 75 of the members are advanced swimmers. 47 of the members are intermediate swimmers. The remainder are novice swimmers. 40 of the advanced swimmers practice 4 times a week. 30 of the intermediate swimmers practice 4 times a week. 10 of the novice swimmers practice 4 times a week. Suppose one member of the swim team is chosen randomly. Okay, so let's take a look at this. This is a lot of information. So I'm going to organize this information with a table, a contingency table, because that will help me. So I'm going to have advanced, intermediate, and novice swimmers, because I'm told that I have 75 advanced swimmers. I have 47 intermediate and the remainder are novice swimmers. Well, we know the total is 150. So 150 minus 75 minus 47 to find what's missing here is 28 novice swimmers. Okay, 150 total swimmers here. So then 4 times a week. So 4 times a week, practicing 4 times a week. Okay. So again, I'm going to look. If they practice 4 times a week, it said novice, the remainder are, okay, 40 of the advanced swimmers practice 4 times a week. 30 of the intermediate swimmers practice 4 times a week. And 10 of the novice swimmers practice 4 times a week. Okay, So the total that practice 4 times a week, we can go ahead and add that up because we might need it. So 4, 5, 6, 7, 8. So 80 practice 4 times a week. Okay, so now I have lots of my information. My information is organized. So what is the probability that the member is a novice swimmer? Okay, so novice swimmer is 28 out of the total swimmers is 150. Okay, and remember, you should reduce if you can. Okay, reduce if you can. So here I reduce to 14 over 75. What is the probability that the member practice 4 times a week? The member practice 4 times a week. Okay, so the total number of members who practice 4 times a week was 80 over the total number of swimmers was 150. And that can reduce to 8 over 15. What is the probability that the member is an advanced swimmer and practices 4 times a week? So 4 times a week and advanced is 40 over 150 total. Okay, so that reduces to 4/15. What is the probability that the member is an advanced swimmer and an intermediate swimmer? Are being an advanced swimmer and an intermediate swimmer mutually exclusive? Why or why not? So the probability of being advanced and an intermediate swimmer is not possible, right? You're either advanced or you're an intermediate swimmer. So the probability of advanced intersect intermediate equals 0, which lets us know that this is mutually exclusive, right? Because that's the rule for mutually exclusive. Okay. Are being a novice swimmer and practicing 4 times a week independent events? Why or why not? So we can check any of the independent rules. We just looked at one independent rule where we look at the probability of being a novice times the probability of practicing 4 times a week. We found both of those values, right? So that was 14 over 75 times 8 over 15, which equals 112 over 1125. You do top times top and bottom times bottom when you do fraction multiplication. Okay, and then we know the probability, we can find the probability of n intersect 4. Okay, we had 10 out of a total of 150. So that's 1/15. Okay, and if you're not good at comparing fractions, go ahead and do your division here. 112 divided by 1125 gives you 0.0996. And 1 divided by 15 is 0.0667. And so these two values do not equal. So since they aren't equal, the answer is no. Okay. All right, let's look at 317. Felicity attends Modesto JC in Modesto, California. The probability that Felicity enrolls in a math class is 0.2, and the probability that she enrolls in a speech class is 0.65. The probability that she enrolls in a math class, given that she enrolls in a speech class, is 0.25. What is the probability that Felicity enrolls in a math and speech? So we're going to use this formula here for math and speech. So the probability that she enrolls in a math class, given that she enrolls in a speech class, was 0.25 times the probability that she enrolled in a speech class is 0.65. So 0.25 times 0.65 gives us 0.1625. What is the probability that Felicity enrolls in a math or speech class? So this time we're using this formula. Isn't it nice that these formulas are already given? Remember, it's the probability of both of them minus the probability of the intersection. And so the probability that she enrolls in a math class is 0.2, plus the probability that she enrolls in a speech class is 0.65, minus the probability that she enrolls in both classes is 0.25. And so the probability that she enrolls in either one of those classes, the OR version, is 0.6875. Are M and S independent? Okay, so we're checking if the probability of M given S equals the probability of M. And the answer there is no, right? We know that the probability of a math is 0.2 and the probability of M given S is 0.1625. So the answer is no. Okay. Are M and S mutually exclusive? So what we're asking is M intersect S equal to 0? And we know that it is not. It's equal to 0.1625. So the answer is no. Okay. All right. Let's look at example 3.18. Studies show that about 1 woman in 7, approximately 14.3%, who live to be 90 will develop breast cancer. Suppose that of those women who develop breast cancer, a test is negative 2% of the time. Also, suppose that in general population of women, the test of breast cancer is negative about 85% of the time. Let B equal women develop breast cancer and N test negative. Suppose 1 woman is selected at random. What is the probability that the woman develops breast cancer? So the probability of B. So that was given to us as approximately, the chances are approximately 14.3%. So we need to change from a percent to a fraction form. So that's 0.143. What's the probability that the woman tests negative? So the probability of testing negative for breast cancer, okay, is 85. Breast cancer is negative in about 85% of the time. Wait, it said test negative? Yeah, okay, so that's 0.85. Okay, given that the woman has breast cancer, what is the probability that she tests negative? So we want the probability that she tests negative given that we know that she has breast cancer. Okay. And so for this one, it says, suppose that of those women who develop breast cancer, a test is negative 2% of the time. So that's 0.02. What is the probability that the woman has breast cancer and tested negative? So C, we want the probability that they have breast cancer and tested negative. So we're doing the intersection. So our formula for that is the probability of B times the probability of N given B. So we have 0.143 times 0.02. So we get 0.0029. So D, what is the probability that the woman has breast cancer or tests negative? So the probability of B or, I don't know why I put a C there instead of an N. I don't know what I was thinking. Okay. Probability of B or N. Okay. So we know that that formula is the probability of B plus the probability of N minus the intersection of the probability of B intersect N. So the probability of B was 0.143 plus the probability of N was 0.85 minus the probability of the intersection, which is what we found in C, was 0.0029. So the probability of B union N is 0.9901. Let me write that a little nicer. 990. There we go. Are having breast cancer and testing negative independent events? And by now you should know what justifies independent events, and you should be able to tell me no. And are the breast cancer and test negative mutually exclusive? Also no. Okay. So the last example we're going to do for chapter 2, like I said, these are not the only examples in chapter 2. You can go back and read your textbook. I encourage you to do that regardless, but you can go back and read your textbook and see that there are several more examples that you can practice, and the answers to those examples are provided to you in the textbook as well. So let's continue. Refer to the information in example 3.18. P equals test positive. Okay. Given that a woman develops breast cancer, what is the probability that she tests positive? So we want to find the probability of P given B, which equals 1 minus the probability of N given B. Okay. Because you can't test negative and positive. So this is going to be 1 minus 0.02, which equals 0.98. What is the probability that a woman develops breast cancer and tests positive? So the probability of B intersect P is going to be the probability of P given B, which we just found, of 0.98, times the probability of B, which we found, which was given to us, is 0.143. And so we have 0.1401. What is the probability that a woman does not develop breast cancer? So we want the probability, the complement, right? So we have 1 minus the probability of B was 0.143. And so we have 0.857. What is the probability that a woman tests positive for breast cancer? So we want to find that probability again with the complement. So we have 1 minus 0.85. So 0.15. Okay, so that concludes our chapter 3. That concludes our chapter 3 lecture. So make sure that you are actively working on your homework, and I hope that you have a great week.